Okay, so our goal is to find the Maclaurin series for f of x, this binomial raised to some power, and we're going to arrive at the formula for the binomial series. K is any power as long as it's a real number, so it could be positive or negative. Also keep in mind x is the variable, and if I'm saying Maclaurin series, then I'm automatically saying about Taylor series about x equals 0. So once I establish all my derivatives, I'm going to evaluate them at 0 to get this guy over here, and my pattern will hopefully help me figure out what to put there because it's about 0. Remember, there's an x minus 0 to the n here. So opening up, I basically need to have these coefficients to be able to come up with the Maclaurin series for this guy for any k I want. So we'll start with the function, and then we'll start differentiating it. So all we did was apply the power rule, since this is some real number. Differentiate it, bring it down, knock down a power times the derivative of the inside, which is just a 1 anyway if I do the chain rule. Let's continue this a few times. So each time, bring down the power, knock 1 away, bring down the power, and knock 1 away. Now we're going to try to see a pattern for the nth derivative. So based on what happened here, I definitely have these guys building up, and then I have to stop at some point and have x to the k minus something when I'm in the nth spot. So I'm going to write these out for sure, they're going to be there. Then I'm going to have somebody that comes right before, and this is going to be, it looks like, k minus n. Why is that? Because, let's start here. I had a k minus 1 for the first derivative, a k minus 2 for the second derivative, k minus 3 for the third derivative, k minus 4 for the fourth derivative, so I must have a k minus n for the nth derivative. Let's try to establish where I would stop by following the pattern. So in the first derivative, I had a k for the guy right before my binomial. And for the second derivative, I had a k minus 1 actually, so I could think of that k as k minus 0 if I want. For the third derivative, I had for the last guy a k minus 2 for the third derivative. For the fourth derivative, I have a k minus 3. So let's analyze those. So to establish a pattern, I guess, I said I could put like a k minus 0 if I want for the first one. K minus 0, k minus 1, k minus 2 was my stopping point, k minus 3 was my stopping point. So at the fourth, I'm stopping at minus 3, at the third at minus 2, at the second at minus 1. So it's going to be some k minus some business. But the guy I'm stopping at is, I guess, 1 less than my derivative. 2 is 1 less than 3, 1 is less than 2, 0 is 1 less than 1, and 3 again is 1 less than the fourth one. So I have options here. I can think of that as it's not k minus n, because if it would be k minus n, these guys would be the same. This is actually bigger than minus 4 by 1. I can say I'm actually stopping at k minus n plus 1, because at negative 4 plus 1 is negative 3. At negative 3 plus 1 is negative 2. At negative 2 plus 1 is negative 1, and so forth. So I can say I'm stopping at k minus n plus 1. Or you can think of it as you're stopping at k minus 1 less than this guy, the previous term before, which if you distribute the minus, it's actually going to be k minus n plus 1. So your choice how you want to look at it. It looks like the last guy we stop at is going to be k minus n plus 1. Again, comparing these guys might be easy for you to see that all I did was I added 1 to the k minus n. Or you're stopping at k minus n minus 1 really, and you distribute the minus and you get the same thing. So the idea is that if I continue to take derivatives, that's where I end up at. Let's go keep track of our counter. So the 0th spot, first spot, second spot, third spot, fourth spot, and the nth stop. Keep in mind x is just the value you're going to choose to put in, which will be 0 for the Maclaurin series. K is just some constant, some number, and n is the number of times I'm differentiating this thing. It's my counter for differentiation. So before I take this nth version of and plug it in here, let me evaluate these guys at 0. So all that happens is I end up with, I should actually fix these guys. This is just 1 plus x to the nth. I have a mistake here. Let me fix those. Okay, that looks better. I put the 1 plus x's there. I realized I had a mistake because I panicked for a second when I put in 0 in there. If that was an x to that power, that whole thing would be 0 and wipe everybody out. So that's how I caught that. It's 1 plus x, so every time I put in a 0 in there, I get a 1. Put a 0 in there, the only thing left is a k. Put a 0 in there, you just have 1 to whatever, k and k minus 1 are left. Put a 0 there, only these coefficients left, 0 there, only those coefficients, and so forth. So for the last one, when I put x equals 0, all these string of things multiplied out are left at the beginning. Now each one of these are going to contribute to these coefficients here. So I'm going to go fill them in one by one, and then we'll come up with this general thing that we are kind of already know. I could potentially pull this guy, because that's my nth derivative as 0, and put it there, but I'll look at it in both ways. So this is it expanded out, going on forever and ever. So I'm going to go put in f of 0, which is that guy, put in f prime of 0, which is this guy, f double prime of 0, which is this guy, just so we can see visually what the expanded version looks like to get a feel for it, before I just go shove all of this in here and say, there it is, I have a formula for it. So I have everything plugged in. F of 0, f prime of 0 was just k over 1 factorial, f double prime was k minus 1 over 2 factorial for the third derivative, and so forth. So this is useful because it's easier, all of those guys of course got pulled from here. It's easier to visualize what's happening just instead of looking at it in closed form. And this of course is going to go in here shortly, and we're going to try to get a closed form for it. Now at the x being power of 1, and if you've gone up to n equals 1, so let's label our counter quickly too. When you're up at x to the 1, you have just a k, one item. When you're at x squared, so when you're at n equals 2, you have 2 items in the numerator, a product of 2 items where the next one has only gone 1 down from the previous one. When you're in the third step, so if you're stopping at up to n equals 3, what's happening? In the numerator, you have 3 items being multiplied. So first one always 1, second one for x to the 1, 1 item, 2 items for the product. For the third one, 3 items for the product. For the fourth item, you would have 4 items in the product. And for the nth one, you have n items in the numerator for the product. Now let's go put this in summation notation, but just keep in mind that the first one has no k's at all, so I might have to write that out by itself. So 1 plus x to the k, we were in search of this guy right here, Maclaurin series, and we sort of found a pattern for the nth derivative. So here is basically where we're at, and I'm focusing on this guy having a power series of this form so far. Now let's quickly repeat why I left the first guy by itself, because if I'm keeping track of my counter, if let's say n is equal to 1, what does this guy tell me to do? It says plug in n equals 1 to see where you would stop at. So this is the guy that I always stop at. That's the last guy. And if I put a 1 in there, I get k minus... So if n is 1, I go up to k minus 1 plus 1. These guys cancel. I will only go up to k when n is 1. You can see that here. I only had a k. When n is 2, I will go up to, let's see what, k minus 2 plus 1. So I will go up to k minus 1, which means I will have the k item and k minus 1, the next guy. So my product will have k and k minus 1, and that's what happened over here. Let's do one more. When n is 3, I will stop at this last guy, k minus 3 plus 1, that's actually k minus 2. So I need to keep going in my product until I get to k minus 2. And then I stop. So at n equals 3, I've stopped up to k minus 2, which is definitely the case. Now if n is equal to 0, and I put 0 in there, I get a k minus 0 plus 1, which is k plus 1. That doesn't make sense. It doesn't fit the pattern because you were starting at k and you kept going down. So putting 0 doesn't fit the pattern, therefore I'm going to have the 0th term, the first item, by itself. Now the thing is, for the binomial series expansion, you may see this guy, these coefficients, written a different way. In you might remember from combinatorics or pre-cal or probability that there's a notation that involves factorials called n choose k business. If I write it in terms of those coefficients, then by definition of something there, I could squeeze this guy back in there. So if you understand this, this is perfectly fine, it's good enough. But we'll throw that notation in there as well. But you don't really need it. You could just work with this. So you may remember this notation from, again, before, maybe from pre-calculus. K choose n, the number of ways you can choose n items from a set of k items. K choose n is how it's read, is really defined to be k factorial over n factorial times the difference of these guys factorial. So for example, 5 choose 2 would be written as 5 factorial over 2 factorial times 3 factorial. This number will give me the number of ways I can choose 2 items from a set of 5 items. I want you guys to notice something here because that'll help us rewrite this. I can write this as 5 times 4 and then stop at 3 factorial because I got the 3 factorial down here. So I'm going to end up with 5 times 4 over 2 factorial, which kind of looks like you're cutting your factorial short at some place. You're not going all the way down to 3, 2, 1, which is essentially what's happening here. This almost should give you a k factorial feel, but you're not going all the way down to 3, 2, 1. You're kind of cutting it short and stopping before you should get to 3, 2, 1. Like I did here, I went 5, 4, and then the rest of my factorial got picked up by what was in the denominator and they canceled. So using this idea, let's go replace that to represent it like this. So I'm going to take this guy and say it's k minus 1, k minus 2, dot, 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 all the way up to k minus n plus 1, and then I will have k minus n and pick up the rest. So all I did was I rewrote this guy as its sort of factorial version, opened up all the way, but not quite all the way. I stopped 1 before k minus n, like k minus n being like my 3 here. So the guy right before it was 1 more than it, k minus n plus 1. It was like this 4 guy. All over this other business that's in the denominator. And notice what happens. This goes away with that. So I really have all of this picking up all of these guys as I need it. So this is really a notation, binomial coefficients is what they're called, k choose n. So n will be my counter, 0, 1, 2, 3, 4, and so on. And since, by this definition, k choose 0 will be k factorial, their 0 factorial, their difference factorial, and it'll be 1, this new notation will actually help me pick up the 1 also. So I can rewrite this guy with these being represented as this coefficient. So short version, 1 plus x to the k could be written as k choose n x to the n, meaning k choose 0, k choose 1, k choose 2, k choose 3, dot, 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 and so forth. And each time I'm doing the k choose 0, k choose 1, k choose 2, and all that business, I'm spitting these terms out. So, if you understood all of this, great. You can think of it like this. If you did not, and this was confusing, that is okay. It's not the end of the world. You can literally look at it in this version and spit out all the terms like this. So in the next video, we will discuss the radiance of convergence of this thing, and then also do some examples to see how this thing works.